Hello students, you might have already watched the previous video that I have posted to you. In that video, I have demonstrated how to determine the coefficients of series solution of harmonic oscillator. And in that video, I have also shown why the very form of those equations, those coefficients, demand the simultaneous existence of two series solutions, one having only odd coefficients while the other having even coefficients only. Now, if we are studying a quantum mechanical system, our ultimate aim would be to determine the eigenvalues and eigenfunctions of the system. In this video, I will explain to you how to determine the energy eigenvalues and eigenfunction of a harmonic oscillator. So these were the equations which we derived in the last lecture, and these are the even and odd solutions to the harmonic differential equation. And if you carefully look at these two solutions, you can see that you have a large number of terms here. It continues forever, and this is also obvious from the previous lecture's power series expansion, in which the summation is from 0 to infinity. So now if this equation and this equation has infinite number of terms, then that essentially means that your k approaches infinity, which means k is very large. So if k is very large, then in this equation the numerator will be 2k, because you can ignore 1 and minus 1 lambda due to the reason that k is a very high value. So this equation will be ak plus 2 by ak equal to 2k. So this will be the numerator, and denominator, in the denominator you have k plus 2, which will become k because 2 is very small compared to k, and this will be approximately equal to k as well. So it will be k into k, and you will get a k square here, and the ratio of the coefficients will be 2 by k. So let's label this as equation 11. Now we are going to do something that might appear like it has no connection with the mathematical methods adopted so far. We are going to write the Taylor series expansion of e raised to x. It will be e raised to x equals 1 plus x squared by 2 factorial plus x cubed by 3 factorial plus etc. It continues like this, and this will be summation m equals 0 to say L x raised to m divided by m factorial. Now, since you know the Taylor series expansion of e raised to x, it will be easier for you to write the Taylor series expansion for e raised to y square. This will be summation m equals 0 to infinity y raised to 2m divided by m factorial. Okay, so now we are going to substitute k for 2m. Then e raised to y square will be summation y raised to k divided by m will be k by 2 factorial. And the summation will be having only even terms, because when m equals 0, the summation here should be for k, right? So k is 2m. When m is 0, k is 0. When m is 1, k is 2. And when m is 2, k is 4, and it continues for all even values. Now this will be equivalent to okay, sorry, let's label this as equation 12. Now we are going to find the ratio of the coefficients of successive terms of this series. So the coefficient of the k term and the k plus 1 term, we have to determine that. The coefficient of the k term of this series would be 1 by k by 2 factorial. This is the coefficient of the kth term, and the coefficient of the k plus 1th term will be 1 by k by 2 plus 1 factorial. Okay. Now the ratio of the k plus 1 to the kth coefficient will be k by 2 factorial divided by k by 2 plus 1 factorial. Let's expand this factorial. It will be, the first term will obviously be 1, and this will continue, and let's write the last few terms of the factorial. It will be k by 2 minus 2 factorial into k by 2 minus 1 factorial. Sorry, the factorial won't be here. K by 2 minus 2 into k by 2 minus 1 into k by 2. In fact, it ends here. So that was all about numerator. Let's see what's the case of denominator. It will start with the 1, and the last few terms will be k by 2 minus 2 into k by 2 minus 1 into k by 2 into k by 2 plus 1. So all these terms will get cancelled, and the ratio of the coefficient will be simply or approximately 1 by k by 2 plus 1. Now we know that k is very high. In that case, this will be approximately equal to 2 by k, because this is 2 by k plus 1, and k plus 1 is approximately equal to k, so you will get 2 by k. Now it becomes obvious that why we have gone for the Taylor series expansion from random exponential term, right? Because the ratio of the coefficient of the exponential series of series expansion of e raised to y square is the same as that of the coefficients ak. The ratio of the coefficients of the Hermite polynomial, the series expansion of Hermite polynomial, is the same as that of e raised to y square, which means that you can replace the harmonic term in your asymptotic solution by e raised to y square. Let's see how this is done. So what is your solution? Your asymptotic solution is psi equals e raised to minus y square by 2 into hy, right? Now we know that the coefficients of hy, the ratio of the coefficients of hy, coefficients of successive terms of hy varies similarly to that of e raised to y square. So in essence, you are actually replacing hy with e raised to y square. In that case, this will be exponential minus y square by 2 into exponential y square. So the wave function in this case changes similar to e raised to y square by 2, right? If you see the power series that we wrote here, okay, so this solution will actually vary like e raised to y square by 2. However, the following solution will vary like y into e raised to y square by 2. Now this is a problem. Your odd and even solution are varying differently. The coefficients of the odd solution, the ratio of the coefficient of the odd solution is different from the ratio of the coefficients of the even solution. This cannot happen. Now this can be solved if we actually terminate this power series after a few terms. So there should be a criteria based on which this termination has to be done. Let's see what that criteria is. Let's assume that the series shown earlier in equation x3 terminates after a few terms. Say when k equals n, it terminates. In that case, when k equals n, the denominator in equation 10, which is 2k plus 1 minus lambda, it has to be 0, because we are not in the series has terminated after n, and for n plus 1, n plus 2, n plus 3, etc., you will not have any coefficients. There are no terms. Okay, so the series terminates at k equals n, and therefore the denominator in equation 10, which is 2k plus 1 minus lambda, should be equal to 0 when k equals n. So this essentially means that this k has to be replaced with n, that is 2n plus 1 minus lambda equals 0. Now we know the value of lambda, right? 2n plus 1 minus lambda is 2e by h cross omega, and this will be equal to 0. Now rearranging, you will get e equals n plus half h cross omega. So we have to add an n here to show that you will get different energy values for different n. Okay, so what happens? This is a very important result in physics. It has far more implications than many important discoveries. I will explain to you that later, but let's have a look at this equation. You have n plus half h cross omega as your energy value, as the energy eigenvalues of the harmonic oscillator. So what happens when n is 0? When n is 0, this will be E0 equals half h cross omega. So E0 is actually the ground state of the system. So this means that even when the system is in the ground state, it has some energy. So this is in sharp contradiction with the results of classical mechanics, which says that E0 equals 0. This is also a result of an after effect of the uncertainty principle, because if E0 is 0, it means that you can calculate the position and momentum simultaneously with accuracy, which is not acceptable in quantum mechanics. So you're saying that even if the system, your harmonic oscillator, is in its ground state, it has got an energy, unlike the classical mechanical prediction. Consider the case in which gas molecules are sealed in a container, and you bring down the temperature of the container, and at absolute 0, do you expect the glass molecules to have complete orderliness? It will not be there. A complete orderly state will not exist. That's simply what the 0 point energy states. Also, this has got a connection to the quantum vacuum, and the term later was popularly called the quantum vacuum fluctuations. And virtual particles, you know that the scientists believe that the entire vacuum vacuum has got some fluctuations, and due to that scientists believe that there exist virtual particles in quantum vacuum, and this zero point energy has a connection to that. I won't discuss that aspect here because it is beyond the scope of this lecture. So this is the energy eigenvalues for a harmonic oscillator. En equals n plus half h cross omega. You may label this as equation 30.